Welcome back to Real Analysis. Today we're going to do two big theorems that you'll remember from calculus class. The first one is Taylor's theorem, and that's kind of the theorem that leads us to Taylor series. And we'll talk about Taylor series later next week. And then the other one is L'Hopital's rule, and I know it's not El Hospital as much as we want it to be. It's L'Hopital. Some people write it with or without the S. Although I will say, I think if I were ever to become a wealthy philanthropist and build a hospital, I might have to shape it like an L and name it the L Hospital. But at any rate, maybe I think that's not ever gonna. I'm not ever gonna have to worry about making that decision. Okay, but let's talk about the two theorems. There's one bit of notation that that I didn't introduce last time that I probably should, and it's that when mathematicians write C1, what they really mean is they mean that the function has this many derivatives. So if we say Cn, it means the function has n derivatives, and each derivative is continuous. So C1 means that the function has a derivative, and that derivative is itself a continuous function. And it's really nice when you can know how many derivatives a function has and whether or not those functions are derivatives. So this is a pretty common notation. And the other common notation that you'll see is C infinity, and you can probably already guess what that means. That just means that the function can be taken derivatives infinitely. So you can take as many derivatives as you want, and each of those is continuous. And let me say, the way we think about these is we think of these more as like sets of functions. So people will say, like, instead of saying Cn is in derivatives, we might say Cn is the set of all functions such that it fits this definition. So usually we think of this as a set. So people will talk about the set of Cn. Okay, so there you go. There's a little bit of notation, and when we say Cn or C infinity, we always have kind of a domain attached to that. So it's Cn on the interval a to b, or C infinity on R, the entire real numbers. So usually tells us about how many derivatives, whether or not they're continuous, and what the domain is. Okay, with that, let's go ahead and tackle our first big theorem. And this is Taylor's theorem. And as you can see, I'm getting a little bit more lazy as I write these things out. So given the hypotheses in the textbook, so you can look it up. This is theorem 4.24 if you want. The hypotheses are not too exciting. It's just saying that we have some interval, a, b, and it said, well, a and b could potentially be infinite. So this could be the entire real line, but just some open interval. And our function is, and then we have a function that goes from a and b, and that's that function f. And the function has to have at least n plus 1 derivatives, and we see that needs to be the case. Otherwise, our whole problem falls apart because we need an n plus 1 derivative for the equation. Okay, so that's kind of at the heart of the hypotheses that go into this. And then once you have the hypotheses, what our theorem says is that for any x and x naught, so this is for any point in our interval, and then some secondary point, so we end up writing the function in terms of x, but it actually doesn't matter how we label these things. For any point, and then a secondary point, x naught, there exists a c such that f of x equals f at this point plus the sum of all these derivatives plus whatever that individual point is right here. Okay, this may look a little strange, but it turns out that what we're really doing is each of these derivatives here, each of these k derivatives, are kind of generalizing the big idea of calculus, and that is that you can estimate the function with just one, just a single, with a line and then a parabola. So let me talk a little bit about the idea of what's going on here. Okay, so if I move my f of x naught over to the other side, I would have f of x minus f of x naught equals, and then we would have the sum of all these derivatives over k factorial x minus x naught to the k. Well, notice what's going on here if, say, n is equal to 0. Well, if n is equal to 0, then we just get f of x minus f of x naught equals, well, if it's 0, then, let's not make it equal to 0. Let's make it equal to 1. So if n is equal to 1, then we get f of 1 over here. And notice this series starts at 1. So we get the first derivative, f prime of x naught times x minus x naught. So this ends up being our equation. And if you look at this, this looks a lot like our mean value theorem. And so this looks a lot like our mean value theorem. And that's because what is the mean value theorem really saying? The mean value theorem is really saying something about if you have 2 points and a line that goes through them, it's saying something about the slope of the function in that range. And so particularly we're kind of learning something about how steep and how the slope works here. Well, and importantly, this function, if you'll remember back to calculus class, maybe I should have left the x naught on the other side. We'll say f of x equals f prime of x naught times x minus x naught plus f of x naught. And then what you see here is we have an equation of a line. So this is our slope, and then we've got mx, and this is like a y-intercept over here, except we centered it at 0. So what happens if we start adding more terms? Well, as you add more terms, it's like we estimate our function with larger and larger polynomials. So, for example, if we're just going to have n equal to 1, then if I have some curve, say, that looks like this, and I have this point, say x naught, if I'm going to do n equals 1, then that means I'm going to estimate it with some sort of curved line here. Well, what Taylor's polynomial says is if I estimate it with that curve, then I actually know something about the difference, and that is there's some c in here. So if I pick an x value, then that means there's some c in here that I can estimate that there's some c in here that if I put it in this equation, that tells me exactly how different these two values are. So it's giving us some bound on the error between this polynomial and our function itself. So you'll notice they're not exactly the same. Okay, well that's interesting. What happens if instead I do n equals 2? If instead I do n equals 2, then instead of estimating this thing with a line, then what I'm estimating it with is a parabola. And so I make like an estimating parabola that does a little bit better job. And then what if I do n equals 3? Then I have like my estimating cubic, right? And so what's happening is as n gets better and better, I'm trying to estimate this point as closely as I can with higher and higher polynomials. And that's exactly what this thing right here is doing, because you'll notice our power of x keeps going up, so that means we're going from an x to the first to an x squared to an x cubed to an x to the fourth, so we're getting higher powers of x. And then these derivatives are kind of telling us what has to happen. But that makes sense because the first derivative kind of tells us the slope. The second derivative tells us something about like the rate of change of the slope or the concavity, which notice that a parabola is completely determined by, if you know the slope at a point and the concavity at a point, then you know how the parabola works. As you get higher and higher, you get further and further into this idea where the powers are becoming higher, and you need the slope, you need the concavity, you need the third derivative. I remember there's a term for that. Maybe kurtosis is one of them. I always get all these terms mixed up, and especially when I've got the camera on and I'm trying to speak quickly and clearly, it never comes out. Okay, so I know what you all are saying right now. You're saying, well, that's great, Dr. Fisher. What I really want to do is prove this theorem. Okay, well, I know that what you really want to do is prove the theorem. So let's talk about how we're going to do it. So first, as I look at the theorem, what I see is there exists a c such that this equation is true. any problem any kind of theorem that's saying there exists a c, you can almost guess that you're either going to go back to the intermediate value theorem, or you're going to go to the mean value theorem, or more than that, you might have to go to the generalized mean value theorem, which, by the way, some people call Cauchy's mean value theorem. So we have all these mean value theorems that we had through the course of the term, and it turns out that today the one we're going to want this generalized mean value theorem. And that's and this is by taking two functions that you might have been able to guess, but it would have taken probably several tries before you would have came to this conclusion. Okay, what we're going to do is we're going to split this fancy equation up into two different pieces, two equations, and then we're going to use the generalized mean value theorem to get the relationship between those two equations. And again, it's not exactly intuitive. So if you're kind of saying, where'd you come up with those equations from, consider yourself pretty normal. Okay, so the first thing I'm going to do is I'm going to like move this x equal to 0 and put like negative x plus. So I'm going to like move that x onto the other side of my equation so everything's equal to 0. And then I'm going to just split this up into two pieces. This first piece right here will be called capital G, and this second piece here will be called capital F. And it turns out that if these are our two functions, then we're going to be perfectly fine. Now, it's not exactly capital G and exactly capital F, but it's kind of pretty close. And so we're going to make these functions in terms of a second variable t, and I know this is going to seem a little bit strange, but it'll all work out in the end. So hopefully this makes a little bit of sense. So our f of t is going to be the second function. So f of t is going to be little f, the n plus first derivative of little f of, oh, wait. That's not what I want for f of t. Yeah, okay, so let me go just a little bit further. So f is this, but I'm actually going to just include this part because this f prime of c is what I'm looking for. So I don't want to include this in either of my equations, right? Because I'm going to have something that's equal to that. So f of t is going to be this kind of difference quotient up on top. So it's going to be x minus t to the n plus 1 power divided by n plus 1 factorial. And the good news about f of t is that its derivative is pretty easy to take. So its derivative in terms of t is just negative x minus 1 to the n over n factorial. Notice your n plus 1 comes down. It cancels with the n plus 1 from the factorial. You still have n factorial left on bottom, and you have an n on top. Negative 1 is from the chain rule. Okay, hopefully that makes a little bit of sense. So now let's come and talk about g, which is the more complicated of the two. Okay, so g is all this stuff at the front. So the way I'm going to define g is I'm going to define g as follows. G is going to equal f of x, and it's going to be a function of t again. G of t is going to be f of x minus f of t. So notice all I'm going to do, actually I said that a little backwards. All I'm going to do is I'm going to move all of this stuff to the other side of the equation. I kind of lied about which side of the equation we're moving on, but it's the same thing. It's a similar idea. Minus f of t minus this sum as k goes from 1 to n of f to the kth derivative of t all over k factorial times x minus t to the k. So what you'll notice that I did with these two equations is I just consistently swapped out all of my x naughts for t values instead of x values. And so I'm thinking of this x naught value as being like a variable that's moving around, and then I'm trying to estimate everything at the point x. So you can kind of see how we're thinking about this. Okay, now we got to figure out this derivative because we're going to want to use the mean value theorem. So this derivative is going to be something we're going to need to take. So notice, right, the mean value theorem gives us a relationship between the derivatives and the values of the function. So let's take this derivative and see what we get. This one's a little messier, but notice it's a derivative with respect to t, so this f of x disappears, that becomes 0. And so we end up with negative f prime of t. And then this part over here on the right is a little bit of a mess. So let me actually move everything over to get myself just a little bit more space. G prime of t equals negative f prime of t minus, and now when I do this sum, I have a product here because I have a function of t times a function of t, so I have to have two pieces on here. Okay, so if I take the derivative of the first, I get the k plus 1 derivative of t, and then and then over k factorial. So those are just constants, so the k plus 1 doesn't... It was real tempting to me to treat this like a power and do k minus 1. But that's not... This isn't a power. This is how many derivatives you've taken. And if you've taken 10 derivatives of f and you take one more, then that's now the 11th derivative. So it's just k plus 1 times the second one, x minus t to the k to the t plus... And now we'll have that first derivative just as it is of t over k factorial. And now the second derivative, this is a power, so it becomes k. And now notice that k and one of those k's cancel each other out. So let's go ahead and make that change here, and that'll help me with my space. So this will become k minus 1 factorial. And then what I'll have left is x minus t to the k minus 1 power. Okay, sorry about my writing, about everything not fitting, but there's one other thing that happens, and that is I get a negative sign. So this in the middle here is actually subtraction. Okay, now let's look really closely at all of these terms, and what you'll notice is that they're actually the same term but one apart. So notice this one, that one is one, that the k plus 1 is 1 bigger than k. The k factorial is 1 bigger than k minus 1. The k power is 1 bigger than k minus 1. Okay, so these are all the exact same terms, except they're just one apart. Well, but there's one other difference. This term is a positive term, and this term is a negative term, right? And this term is a negative term. So all of these pieces are one apart from each other, so they telescope. All the positive ones cancel with all the negative ones, except for the very first and the very last term. So let's go see, and let's see, what is the very first term going to be? Negative f prime of t. And so we see this is minus, well, the very first term is what happens if we put an n in here. And so that's f, that's the n plus first derivative evaluated at t over k factorial times x minus t to the n. And then we go all the way around. So we've got all of those derivatives until we get to the very end, and that's the first derivative. And then that's this term over here. This term on the right is the one that doesn't cancel. So the very last term survives, and it is f to the first, which is f prime of t, divided by 1 minus 1 factorial, 0 factorial, which we all know is equal to 1, times x minus t to the 1 minus 1 to the 0 power. And so what you'll see is that this end term here is actually the exact same as this term, and so this term and this term cancel each other out, and we're left with the final result, which is g prime of t, which is equal to negative f n plus 1 derivative of t divided by k factorial times x minus t to the n. Okay, well that was a mess, and but you all are good at derivatives, so I'm sure you are capable of doing all this. Now what we notice, oh sorry, this k, this is not a k anymore. This is now an n on the bottom. That was a mistake on my part. So the bottom now is n factorial. Now, if you look really closely, you'll actually see something really interesting about these two, and that is this piece right here is the exact same as this piece, and the only thing it's missing is that n plus 1 derivative going on there. And so we can now divide these two. So let's come on to a new piece of paper and divide those two. So what you'll notice is that we have g prime of t divided by f prime of t. If I divide those two derivatives by each other, then what do I get? Well, I get that the x minus t to the n's cancel each other out. I get that the n factorials cancel each other out, and I get that the negative signs that cancel each other out, and the only part that doesn't cancel is this n plus 1 derivative. So when I divide those, all I have is the n plus first derivative of f evaluated at t. Now, maybe now you're starting to see why we went through all this rigmarole, and that's because this piece, f prime divided by g prime divided by f prime, is exactly the piece that we want to put the c in. So this is the part that has the hidden c in it. And it's a g prime divided by f prime, which is exactly what shows up when we do our generalized mean value theorem. So let's come over and talk about that generalized mean value theorem. So what does the generalized mean value theorem say? The generalized mean value theorem basically says that there exists a c in the interval AB such that, and I guess maybe I won't do A and B, maybe I'll stick with the same x and x naught that we've done before. So there exists a c in our interval x to x naught such that, and so what the generalized mean value theorem it says is that g prime of c divided by f prime of c is equal to g of x minus g of x naught divided by f of x minus f of x naught. So in other words, if I take this f function evaluated at the beginning and the end of my interval, and then I take the g function and also evaluate it at the beginning and the end of my interval, the ratio of those differences is the same as the ratio of the derivatives of g prime and f prime. Okay, well, this ends up being pretty useful. So what we need to now go through is we need to figure out what is this g prime of x minus g prime of x naught, and what is this f prime of x minus f prime of x naught. Okay, so let's go through those things, and to do that, I'm just going to flip back to the previous page, and I'm going to erase a bunch of stuff because I know what those derivatives are. So let's just kind of try to keep our original functions and make some observations. Go, well, what is f of x and what is f of x naught? Well, capital F of x. What happens if I put an x in this equation? I get x minus x in the numerator, so capital F of x is 0. And what is capital F of x naught? Well, it is just x minus x naught to the n plus 1 divided by n plus 1 factorial. Okay? Okay, well, let's come over here and say, well, what is g of capital X? Well, g of capital X, well, this ends up being f of x minus f of x, so this part right here ends up going to 0. And then x minus x, so this part right here ends up going to 0, and so you'll see that everything in our entire equation goes to 0. So g of x is equal to 0. And then what is g of x naught? Well, g of x naught is f of x minus f of x naught minus the sum of as k goes from 1 to n of f of the kth derivative of x naught divided by k factorial times x minus x naught to the k. And what you'll notice is that these pieces are starting to look like the pieces that we want, right? Because this f of x naught term is exactly that, and this g of x naught term is exactly all of this stuff. So we're starting to make progress because these things are looking like the things that we want in the original equation. And now all we have to do is finish putting it all together, because we know that when I turn back to the other page, we're going to have g of x naught, which is all of this on top, divided by x of x, f of x naught, which is all of this stuff on bottom. So let's come to the next page and rewrite it. That means that this term right here, this g of x divided by f of x term, well, notice this was 0 and this was 0. Our minuses cancel each other out to make each other pluses. And so all we're left with is the top, which is, let's write this in black. All we're left with is the top, which is, I don't want to flip back to that page, so I'm going to look on my notes here. which was, oh, come on, which was f of x minus f of x naught minus the sum as k goes from 1 to n of the kth derivative at x naught divided by k factorial times x minus x naught to the k. Well, that was our g term, and our f term was f the n plus first derivative evaluated at x naught. Is that right? So no, it wasn't that. It was just x minus x naught. Hold on, let's look and make sure. Yeah, it was just x minus x naught to the n plus first power divided by n plus 1 factorial. Well, what does the generalized mean value theorem say? The generalized mean value theorem says that this piece, which I've written below, should equal this piece, which I can figure out is right here. So what should this be equal to? This should be equal to f to the n plus 1 at our c value. So we find that c value from the generalized mean value theorem, and now we're ready to just reorganize some things. So I will now move this over to the right. So therefore, f n plus 1, n plus first derivative divided by n plus 1 factorial times x minus x naught to the n plus 1 is equal to f of x minus f of x naught minus that sum from 1 to n of the kth derivative of x naught over k factorial x minus x naught to the k. And now if you look, we actually have just our theorem just as we can see it. So the only thing is they're in different orders. Notice this part right here is by itself, and then these parts have all been moved to the other side of the equation. But when you do that, you get our theorem just as it's written. So we've now, that proves our theorem. So, okay, so that proof, there's a lot going on. If you found like the setup confusing, or maybe you got lost in the notation, that's okay. I'm hoping that we will kind of get more and more maturity at keeping up with really complicated notation and looking at complicated things. But understand that the basic gist of it was using the generalized mean value theorem to find that c value. And you had to be pretty clever in choosing your g and f functions so that the generalized mean value theorem popped out what you wanted it to be. So if you kind of look at this theorem, you're like, I would have never picked this for f and this for g for my problem. Then I would say to you, yeah, you're probably right. I mean, you know, coming up with this theorem and coming up with this proof is a pretty clever thing, something that undergraduates usually don't think of independently. But that being said, you should be at the point where you look at this theorem and you see this, there exists a c part, and you go, oh, I need to be using some sort of mean value theorem. And so if that was your reaction, then that means you're on the right track, because once you know you need to be using a mean value theorem, then you can start hunting for the functions and hunting for how to make that mean value theorem work correctly. So there you go. I hope you enjoyed that. Why do we care? Well, one reason we care is because your teacher tells you to, and it's in the textbooks and all these things. But the real thing is that this part on the right side, so this part over here, let me clear this page, is called the Taylor polynomial. So this right here, you'll notice that this term is actually just the k equals 0 term of that equation. So this part right here, the sum as k goes from 0 to n of the kth derivative x to the 0 over k factorial. And all we have to do is recognize that 0 factorial is 1, and anything to the 0 power is 1, and that the 0 derivative is f, and you'll see this is just f of x. So the 0 term is this f of x naught, and the rest of the term here. This is what we call the Taylor polynomial. And, well, there are lots of Taylor polynomials, and so this is the Taylor polynomial for f of x for f of x, of order, and so you have to pick the order, and so this is of order n, so n tells us how long our Taylor polynomial went on, for f of x at x equals x naught, at x naught. So you have that x naught point, you have the polynomial, and you have that order. And there's a notation that the textbook really likes, and the textbook writes p sub n, and then they write f and x naught up here. I will say this f and x naught, this is not standard. You don't, I mean, maybe it is, but you don't see this very often. Most people, and when I write my homework questions, will just write p of n and then include the f and the x naught in the description of p of n. So we'll say it's the Taylor polynomial p4, the fourth Taylor polynomial, and then the f and the x naught show up from the problem. But if for some reason you needed to distinguish, you had multiple different functions, multiple different Taylor polynomials, this is a good way to do it. And when you see that notation in the book, that's what the book is talking about. Oh, and I guess this is a function of x. Well, what you can see from our equation is that once you know the Taylor polynomial, f of x minus the Taylor polynomial is just this part right here. So that part right here is f of x minus that Taylor polynomial at x. So that kind of gives us a nice idea. The reason is this Taylor polynomial estimates the function f of x. And so you could have some function that's hard to work with, like e to the x or log of x or something like that, which those actually aren't that hard, but something that's not as simple as like an x squared or x cubed or x to the fourth. And you could use an x to the fourth equation instead of e to the x, and we would know how accurate that equation is, because we would know that f of x minus whatever that polynomial is less than or equal to that bound that we had over at the right. So that n plus first derivative evaluated at c over n plus 1 factorial times x minus x naught to the n plus 1. Okay, so this is our bound, and what you can see is we can just take the maximum of all these. We could just take the max of all the c's in whatever interval we're talking about. And if we take the largest c value in our interval, or the maximum of this number for a c interval, then that bounds this polynomial. So we see that now we have some sense of how big our polynomials are. And so importantly, if this derivative is bounded, like if this derivative is always less than 1 or something like that, then this n plus 1 factorial is going to become a really, really big number. And so this bound, this error, might be really close to 0. And so that's what's really nice about this problem. And I'm going to give you a couple tasks at the end of this video, and those tasks are just Calc 1 problems. But part of it is something that we don't always do a lot of in Calc 1, and that is I want you to find this polynomial, but then I also want you to bound the error of the polynomial by thinking what's the largest that the derivative can be within our region. Okay, all right, so now for our second proof, L'Hopital's rule, and we all know L'Hopital's rule. It has the theorems in the book. It has the hypotheses from the book. They're a little more complicated. So we need these functions to be defined on some open interval with a inside of it. So we need to have some open interval with a in the middle. So some open interval that has a in the middle of it. The functions don't have to be defined at a, but they need to be defined at every point except a. So they're defined using the textbook notation at a minus a. The functions need to be differentiable on this entire domain, so the derivative needs to exist everywhere. And importantly, g of x and g prime of x needs to not be 0, and g prime of x needs to not be 0 on this domain. And you can see that if they were 0 in the domain, that'd be a problem, because then we'd be getting undefined points. Now, if they're only 0 a couple times, right, if they're only 0 like once or twice, then you could just make your interval small enough to not contain those zeros anymore. So, but if for some reason, if like g of x was some sort of sine of 1 over x function that's hitting 0 over and over and over again, that would be bad, right? So So it's not allowed to be 0 in this interval that we're talking about. Okay, if that's the case, then what L'Hopital's rule says is that if it's one of these, you all remember it from calculus as the indeterminate forms, 0 over 0 or infinity over infinity. If both the limits are 0 or both the limits are infinity, then you can take the derivative of f and the derivative of g and get the same result. You all, I'm actually pretty confident you all remember this, because this is one of those theorems in calculus that everybody's like, wow, that's so much easier than doing all the algebra, and we really like it. Now, it's not always easier, but sometimes it is. Well, let's talk about this proof. I'm only going to do one of the proofs because, as usual, the book kind of splits up into lots of pieces. We're going to do the proof. There's the proof where the limits are both 0. There's the proof where the limits are both infinity. And then there's the proof where the answer itself is either plus or minus infinity. And these are all different things, so we're not going to worry about all those. We're just going to worry about one case, and we're going to worry about the case where this limit is a real number and these things are approaching 0. So that's the easier case, and I think it's the case that makes the most sense. And then from there, you'll see that you can look at the other ones in the book. The other ones in the book are pretty similar, but they're a lot messier because you have to worry about a lot of other things. Okay, let me kind of give us a little picture, though, of what we're going to do. And this should give you a bit of a picture of why we're going to approach the problem the way that we are. So if I have a function, and g of x and h of x are both approaching 0 at a, it could be undefined here, but that means I've got some function like g. Maybe that's my g function. And then I've got my f is maybe some function like that. So that's my f function. Well, what I'm really asking is what's the ratio between g and f for all these points as we get near to our values. So if I take this ratio and divide them, take that side, what's the ratio as we get there? And if you look at this, it kind of seems somewhat intuitive that this should be connected to the slope of the functions, because if I look at this one, it looks like as we get closer, tell you what, let me draw these functions so that they're even clearer to see. So let's put a right here, and let's let g just really be mostly straight nearby, and f mostly straight nearby. And what you'll notice is that it looks like at every point, g is, I don't know what, almost maybe about 1.5 times whatever f is. So here g is about 1.5 times f. Here g is about 1.5 times f. So you can imagine that f divided by g is going to be about 2/3, right? So f is about 2/3 of g. So f over g is roughly 2/3. And so you should guess that this limit here will come out to be 2/3, right? That's what I would guess if I were to come through this. But what you'll also notice is that this idea of the ratios of these as we get closer, well, since we're getting closer and closer, that's actually connected to these slopes. So it turns out if we look at that slope and look at that slope, then you'll notice that slope m1 is about 1.5 times the slope of m2. And so the ratio between the heights of the points and the ratio between the slopes ends up being the exact same number. And so that's a reason why we should believe that this L'Hopital's rule is actually true. But from there, the way we're going to do the proof is this. We're going to pick a point, and then once we have that point, we know we can find some point in the middle that has the same slope as those 2 points between them. So we'll find a point here that has the slope, and then I'll find a point here that has the same slope as those two guys. How do I find those two slopes? Well, I use the mean value theorem. So you can see that we're actually using the mean value theorem to prove this theorem as well. So we're taking one point and another point and taking a slope at some point in the middle of them. You can also probably guess that because I'm trying to take individual points, I'm probably going to be using a sequence instead of doing something else. So I'm going to have a sequence of points, and then I'm going to have a sequence of slopes found from the mean value theorem. And what I'm going to claim is that those points have the same limit as the slopes, right? And it seems like they should as we go through here. Okay, so let's actually start tackling this proof. I think it's not one of the worst proofs that we'll do this semester, but I hope that picture gives us a little bit of an image of what we're going to try to do. Okay, so a few things that I'm going to do first. Notice the functions could not be defined at 0, but I'm going to go ahead and define f of 0 and g of 0 to both be 0, because that's what their limits are as they approach 0. So remember, we're doing the 0 case. So I'm going to define both of those to be 0, and once I define them to be 0, then that means f and g are both continuous. And then I'm going to let x of k just be some sequence that approaches a. So x of k is any sequence that I want. It's arbitrary, and it's an arbitrary sequence approaching a. To make things less confusing, I'm going to assume that either x of k is always bigger than a, or x of k is always less than a. So that way I'm really just talking about a sequence approaching from the right or from the left. And notice if those all work, then my right-hand limit and my left-hand limit come out to be the case. But let's just assume, just so that we don't have to do both cases, let's just assume that x of k is always bigger than our a value. So let's just assume we're always approaching from the right. That'll just make life a little bit easier. Okay, so now what we're going to do is we're going to use the generalized mean value theorem for this f of x and this g of x. By the way, the generalized mean value theorem shouldn't be too big of a shock at this point, because we're trying to relate a derivative of one function to a derivative of another function, and then generalize based on the values of the functions themselves. The generalized mean value theorem is a nice equation that gives us a strong relationship between the derivatives of the functions based on the values of the function. So it shouldn't be a shock that the generalized mean value theorem is the way to go. But let's use it. So by the generalized mean value theorem, we know that there exists some ck in that interval in between a and xk. So if I take one of my sequence points and take the difference between it and a, then there exists some c in that region such that the following is true, such that f prime of ck divided by g prime of ck is equal to f of xk minus f of a divided by g of xk minus g of a, and this is equal to just f of xk minus g of xk, and this is just because we assumed that f of a, f of 0, or f of a and g of a were equal to 0. We assumed that they were equal to 0 at those limit points. So these two parts right here are both 0. Notice that you might have to ask yourself a question: can my denominator ever be 0? And the answer is no, because I assumed that g of x was a positive number. That's part of the assumptions. That was from the textbook that I mentioned earlier. Okay, so now that I have this, look, I'm almost done with my proof, because I have this derivative part, which is right here, and the non-derivative part, which is right here, and they're equal to each other. Okay, well, what I notice is now I notice that since this ck value is always between a and x of k, then the x of k's approach a. That means that the c of k's must approach a also. And this is a squeeze theorem problem, right? So c of k's are between a and x. The x's are squeezing to a. The c's also have to go to a also. Well, if that limit exists, oh, and I should have put that, right? So that was one of the hypotheses, is that this equals that, assuming this exists, right? If that limit doesn't exist, then, not only is the theorem not true, but the theorem's kind of pointless, right? So you have to have that limit actually existing. If that exists, and we'll just say equals some number L, assuming that L could actually be infinity in this case, and it doesn't make that big of a difference. If that exists, then the ck values, because it's a sequence, have to approach that same L value as well. And this was something we proved, right? That if a limit equals L, and you take any sequence that's approaching that limit value, then that sequence has to approach L also. Okay, so that's just by the definition of, by the sequential characterization. Well, okay, since the CKs approach L and the these have primes on them. Since f prime of ck and g prime of ck approach L and they're equal to f of x, g of x, then we know that f of xk over g of xk has to approach L also. And so we made this connection between f prime and f, and so we know that because it's a sequence, the ck's have to go to L. Well, that means that the fk's have to go to L as well. But notice, this sequence was chosen arbitrarily, so therefore that limit as x approaches a of f of x over g of x, that equals L also. And that finishes our theorem, because for an arbitrary sequence, it approached L, so that means that the limit itself has to approach L. Okay, what I want you to do for your tasks, first I want you to do two tasks involving Taylor polynomials. So this one is just find the Taylor polynomial. And then the second one is try to find a bound for the Taylor polynomial using that term that we had earlier. And that's because we know what the derivatives of e to the x are. Assume you know how to take the derivatives of e to the x, and also assume some basic things like you know how big e to the x is at different numbers. Okay, so we're going to assume that that's just fine. And then secondly, I want you to find this limit using L'Hopital's rule. This is actually not a limit of the type 0 over 0 or infinity over infinity. This is actually a limit of the type infinity raised to the 0 power. But this is every bit as problematic. So what's my suggestion? My suggestion is to try to use logs. And if you use logs, it will pull this out. And this is something you do in Calc 1 or Calc 2 or somewhere around there. All right? So